silicon. And at the surface is terminated. Usually you have two types of termination. Sometimes it's called arsenic cap, the arsenic atom on top. Sometimes you can get gallium cap. Usually it's arsenic cap. And this arsenic cap is sitting on top. And you would have, of course, they would have this dangling structure, the dangling bond. So this is unreconstructed. Think of it as you freeze your solid, you cut it, and that instant you see this unreconstructed gallium surface atom on there. And now you allow them to reconstruct. You allow the atom to move around, right? And they would go to a lower total energy state, and you see this gallium will be on top of the arsenic will be on top of the gallium. This is why it's called gallium arsenic cap, because the arsenic is on top. So this corresponds to stable. This total energy is more stable than this because it's reconstructed from here to here. And so if you look at the corresponding electronic structure, you have valence band, right? You have conduction band, and for this surface you have a couple of surface states, corresponding to just the periodicity of this surface atom. It generates its own electronic state called surface state in between the band gap, inside the band gap, right? Which you normally don't expect to see any electron there. But if you allow it to reconstruct, these surface states actually change its position because, as it should. Because why? Because the physical position of the atom has shifted, right? We have reconstructed, meaning that it has changed. But the different physical structure, the energy level, of course, will change. So even the conduction band and valence band are the same. Your bulk is the same. These surface states will change. And so this is what you actually see if you measure it. Okay. So this is an example of the surface state depending on the crystallography structure that you see. Okay. And one of the interesting things of this surface state is that there's this band bending effect, so-called band bending effect. It's a very important concept in semiconductor physics. In semiconductor industry, everything is based on band bending. The reason why you have band bending is because you have two dissimilar material. And sometimes, in this particular case, I show you have an N-type semiconductor. So you look at the top one, because of this surface state, your vacuum level, surface state level, you create a band bending because you can feel the electron from all the valence band up to here, right? And so you can see you can do interesting things. This band bending, when you bend this band at the vacuum level, all your bands are bent in the same way. So you bend, both the valence band go this way and conduction band this way. And what happened to this? If you have a band like this, what happened to it is that you have a higher potential at the vacuum level. It means that this electron, which is a conduction electron, cannot leak out. It's trapped. Okay? So now if you can somehow do something to it, like apply a potential or something, right? Modify this potential, lower or higher or so forth, you may be able to eject this electron and create conduction. Okay, so that's the entire basis. This idea of band bending, right? In other words, you have created valence band to be continued with the solid surface state electron. You created this kind of potential. Here I plot a depletion region, right? The reason why this potential goes up is because you have depleted electron in this region, near the surface, the vacuum. So this is vacuum, this is the surface region. And so you have a depletion region, the potential go like this to the vacuum and lower like this. Okay? So this band bending phenomenon is a very powerful concept in building the electronic devices. Okay? So in any rate, so I would like to wrap up. In fact, surface state can be thought of LCAO. So in this case, right, we're talking about this LCAO approach, linear combination of this atomic orbital of just the surface here of the dangling bond state. So we're talking about this dangling bond state here. And they generate these states that we have. Okay, so and this state, like the bow state, can undergo surface reconstruction like this to give you new state, movement of the state. And these state can be changed by surface reconstruction, defects, right, the presence of defect, and also absorbate. So if you put the absorbate on, you crunch these surface state, and the surface state disappeared, and you can tell right away that you have this surface state. Okay, so I'm going to stop here today. So next day I will try to finish up and talk a little bit about the property at the interface related to these surface